Hey everybody, Mr. Bells again. We're going to talk right now about Geometry A. This is from the Big Ideas Math textbook. We're looking at section 4-3 on rotations. Basically any type of object that rotates, and we can rotate it around itself like this. Or we could have the rotation point be someplace further away, like my hand, right? You can see here. And the hand can rotate about this point that's not necessarily on the hand. Okay, so rotating right in the middle of the shape or some other point. And here we go. We're going to use the student journal again. Hopefully this will be beneficial to you guys. If you have one of these things. Let me tighten up my camera here and we'll get started. That was not tight. That was loosening. So here we go. So what is a rotation? A rotation would be like this shape right here. If I rotated it on or around a point, it could go like this, which means it's rotated this direction, which would be a what we consider a negative rotation, but it is clockwise. So counterclockwise is positive, clockwise is negative. And the reason is because used to be positive going the other direction because they talked about rotations before there were clocks. So it was based on how the sun starts in the east and sets in the west. Okay? Now that point also could be, like if I had this flag right here, the point also could be someplace further away where I could then rotate the flag around a point that's not on the shape itself. Okay, so it doesn't have to be there, but the center of rotation is that actual point. And like if I had a square like this, I could rotate it on a point here and have it end up like this, or I could have a square and I could rotate it on a point here, and you'll see that this one we actually has rotational symmetry, which means if I rotated this 90 degrees, that point would end up there, and that point would end up there, and that point would end up there, and that point would end up there. Okay? We know that something has rotational symmetry if we can spin it like that. This one has 180 degree rotational symmetry. Sorry, we're all the way down to here on this one now. If I have, and let's do a whole thing here, assuming all these segments are the exact same length, this has rotational symmetry in 45 degree intervals, because all I'd have to do is rotate it just like that. Okay, the center of symmetry is the point at which that rotation can occur. Good deal. So let's try this. Let's try, does this have rotational symmetry? And the answer is yes. That point right there has rotational symmetry. And if I said this, does this have rotational symmetry? And the answer is no, this doesn't have rotational symmetry at all. I could rotate it, but I can't rotate directly on top of itself. Like if I took this point right here and rotated it 180 degrees, it would end up right there. And if I took this point right here and rotated 180 degrees, it would end up there, and this point here would end up here. And you can see that all those points would go there. But like on this one right here, if I thought that was my center of rotation, then this point right here, rotating at 180 degrees, would end up right there. And there's nothing in that spot, so that's why that doesn't have rotational symmetry. Okay? So how do we do a rotation? Well, we can simply, if I wanted to rotate this thing a certain amount of degrees around this point, just like this, I can connect a segment from here to here. I could use my protractor and measure an angle. Let's say I was going to do it 120 degrees. And I'd open this up 120 degrees. And then I'd take my marks right here and I'd transfer that. So however long this is, I would make it the same length. Sorry, it's probably about right there. And that would be the start of it. And then I would do the same thing here. I would rotate that one 120 degrees, so it would end up out like this, and I'd put that point, and I would end up with all of my flag this way. So this would end up going just like this. Can we see that? and this one here. So this one was off by a little bit. That had to be a little bit narrower, sorry. Maybe like that. And then like this and like this. And you can see that that would rotate 120 degrees. So how do we do some of these rotations without the use of a compass? Can we do it in a coordinate plane? And what does it look like? Yes. So these are ones you just need to know. Okay. So if I take an AB, and again, I don't necessarily like ABs like this. I like when they put x comma y. Take any xy coordinate and make a negative y comma x coordinate. That will be a rotation of 90 degrees. And remember, 90 degrees is a counterclockwise, so that's a positive rotation. Whereas if they do it as x, I'm going to do the bottom one, x comma y becomes y comma negative x, that's a rotation of 270 degrees. So 270 degrees would take us from here all the way to here. But I do want you to know this, and maybe this makes sense to you, that a rotation of 270 degrees also equals a rotation of negative 90 degrees. Because you could see this if I went this way. A negative 90 ends up in the same place as a 270 does. And these ones we already did. We did these in class, right? Changing the A flips it over the y-axis, changing the y flips it over the x-axis. And when we showed this in class, that if I take a shape and I flip it over the x-axis and then flip this one over the y-axis like that, that the end result is a rotation of 180 degrees. And whether or not you want to call that clockwise or counterclockwise, I honestly don't care. Okay? The textbook will talk about something called rigid motion, and rigid motion simply means that the shape that you had in the beginning still looks to be the exact same size. So it is congruent to it. Okay? So here we go. So this one says do a 180 degree rotation. So again, you're just going to take this shape and you're going to flip it over the y-axis and then flip that image over the x-axis. If you want to do a 90 degree rotation, you're going to take all the x comma y coordinates, and you're going to change them. You can see this right here. 90 degrees becomes negative y comma x. Negative y comma x. So all these ones are going to be okay, and I honestly, I don't need you to memorize this in the time of COVID. Put these on your theorems, postulates, properties, definitions, lists, all of these different notations for this. It's really not about perfectly knowing the notations, but it's about knowing what transformations look like, and that the fact that we can coordinatize them, which means put them on here. So let me give you a quick little rundown of why this is important. And when we deal with stuff in data class later and talk about matrices where we can store these things, it's pretty much this coordinatized geometry and these translations and rotations that allow for us to be able to play, yeah, you bet you didn't know this, the video games. So like if you have a little, I'm going to do this really bad. You have a little Mario that's running down the screen like that, then he's really doing a translation. And if all of a sudden the turtles come out and they're snapping turtles, right? That's a pretty bad turtle. Whatever. Then what's Mario going to do? Mario's going to turn around and go the other way. And that would be a reflection. Good deal. And sometimes you know he needs to jump up and hit the little things, right, with the little golden pots. Well, when he does that, from above or from below, he does some rotationary spins. I think Sonic the Hedgehog probably does it a little bit more. I think you guys might know who that is still too. And after we deal with these, what we've done so far, reflections, rotations, translations, glide reflections, there's also going to be something coming up called the dilation. And the dilation allows Mario to grow, or to shrink. So dilations are not rigid motion. Dilations change size, and they can change, we can also do scale factors, so make them really tall with same size heads, or really small with it. So, but we use that a lot in video games, and we store these images of these people in something called a matrix. And we'll deal with that in something called data A. So down here at the bottom, compositions of these things. So reflection in the x-axis, again, just look back, check your notes. What does an x-axis reflection look like? Hopefully you can, maybe you can even do it off the top of your head. So an x-axis reflection takes a normal coordinate xy and replaces it with an x comma negative y, right? And then 180 degrees about the origin, 180 degrees about the origin, takes an xy and changes it into a negative x, negative y, right? So if you can stay on top of those and know that this one over here, this is a translation, right? This is going to move it to the right 2 and down 3. You can stay on top of those ones. It'll make all of this stuff much easier. And then 4-4 over here, we're going to talk about some more stuff. But before we do that, we're going to go here. So this one says, determine whether the figure has rotational symmetry. If so, describe any rotations that map the figure onto itself. So one of the ways that we can tell that a figure has rotational symmetry is if we can spin it less than 360 degrees, and again, the most you can have is 180 because that spins it all the way around. Less than 360 degrees, and points will line up directly on top of itself. So I'm hoping you can see that this could rotate directly to there, right? And this could rotate directly to there, and this could rotate directly to there, and this could rotate directly to there, and this could rotate directly to there. So that means it has 5 different of those rotations, right? So if we take that 360 degrees, which we know is all the way around one time, and we split it into 5 equal parts, we can see that that's 72 degrees. Now, where does the 72 degrees come from? Well, watch. If I put a point right here in the center, and I do this, and I do this, this angle right here is 72 degrees. And I know that because of the fact that I can split it into 5 congruent parts. And 5 times 72 is 360, or 360 divided by 72 is 5. But we'll say this has 72 degree rotational symmetry. Okay? Another reason why I knew that it had rotational symmetry is because I can put in this line right here. Watch this long line right here. That is a line of symmetry, right? And if I put in another one right here through the midpoint of the other side, that's a line of symmetry. Anytime one shape has 2 or more lines of symmetry that intersect right there, that point of intersection is the center of the rotation, and it has to have rotational symmetry. Okay? Now again, watch. Here's a big T. This has 1 line of rotational symmetry, so it does not have, or sorry, 1 line of reflectional symmetry, so it does not have rotational symmetry. But if I did this, wow, that might be the best H that I've done in a while. You can see that this one does have a line of reflectional symmetry, right? But it also has another line of reflectional symmetry. So if you ever have 2 or more lines of reflectional symmetry, it has to have rotational symmetry. Okay? And you can see you can take that H and spin it 180 degrees, and these 2 posts will line up right there, and those 2 posts will line up right there. Okay? So then we go onto this shape right here, and we go, hey, does this thing have it? Well, I'm hoping it's obvious. This has 1 arc, this has 2, this has 3 arcs, this has 4 arcs. So whenever I spin this thing, right, I can never get 4 onto 4 unless I go all the way around. And again, you can't have rotational symmetry of 360 degrees. In fact, the largest you can have is 180. You can flip it like this H completely upside down. You can have smaller increments, but but you can't have that. And you could even have a shape like this, like a circle, right? It has rotational symmetry technically in infinite amount of degrees, because anytime you go a certain number of points, it can keep going. And remember, between any 2 points, like between this point right here and this point right here where it touches, there's an infinite number of points in between there. Okay, so that was 4.3 on rotational symmetry. Hopefully this was really beneficial to you guys. Make sure you at least know the basics of this stuff and know the coordinates that we have. Practice these ones too, and make sure that you do the online assignment. This is Mr. Bells. I will talk to you later.